Hi, this is Jie Zhongqiu from Tsinghua University. It is my pleasure to present our work LightNE, a lightweight graph processing system for network embedding in SIGMOD 2021. This is a joint work with Lexman Julipala from MIT, Jie Tang from Tsinghua University, Richard Peng from Georgia Tech, and Chi Wang from Microsoft Research, Redmond. The code of this work is open source online at GitHub. This talk will start with a gentle introduction to network embedding, and then I will propose LightNE, including its design goal and how we meet the goal with algorithm and system co-design. Finally, we will see some experimental results on very large graphs with billions of edges. Graphs are everywhere around us, including the social and business graphs, biological graphs, knowledge graphs, internet graphs, and transportation graphs. Over the past years, the main focus of graph learning research has been on designing models and algorithms for large-scale and real-world graphs. Among many graph learning algorithms, network embedding, exemplified by deep work, line, and multivector, is one of the most important methods for learning representations for graphs. The problem of network embedding is formalized as follows. Given an input graph G, we want to learn a mapping function F from its node set V to low-dimensional vector space RD, so that the low-dimensional embeddings capture neighborhood similarity and community membership of the input graph. Here is a toy example from deep work. You can see that we can almost reconstruct the graph structure from the low-dimensional embeddings. The idea of deep work is very simple and smart. It borrows the idea from a popular natural language processing method, word vector, by first sampling random walk sequences on the input graph, and then training a word vector model on the sampled sequences. However, as a gradient-based learning algorithm, deep work is not scalable. In the common system designed to accelerate deep work, CPUs are designed to conduct graph operations such as random walk sampling, and GPUs are designed to perform optimization. However, the whole system is bounded by GPU memory, which in most cases is at most 32 GB per GPU. Embedding graphs with billions of vertices often require hundreds of gigabytes of parameter memory. Actually, in a real-world example, Alibaba embeds a 600 billion node commodity graph by first partitioning it into 50 million node subgraphs, and then embedding each subgraph separately with 100 GPU running deep work. In contrast to the mainstream belief that distributed architectures and GPUs are needed for large-scale network embedding with good quality, we prove that we can achieve higher quality, better scalability, lower cost, and faster running time with shared memory CPU-only architecture. To achieve this, we view network embedding from a matrix factorization perspective, rather than treat it as a gradient-based learning algorithm. Our previous work named NetMF shows that deep work is implicitly and asymptotically doing matrix factorization. Factorize a random walk matrix polynomial composed with the entry-wise matrix logarithm. Our another work, LightNE, shows that although the matrix powers could be very dense, but it can be well approximated by sparse matrices. Using the path sampling algorithm with O(m) log n number of samples. Here, n is the number of edges of the input graph, and n is the number of vertices of the input graph. The path sampling algorithm first sample uniform random edge, let's say UV, from the graph, and then conduct short random walk from the endpoints U and V, reach U prime and V prime respectively. And the new edge U prime V prime contributes to the specifier of the R-step random walk matrix. We will follow the above matrix factorization framework to design our LightNE system. Now, I will formally introduce LightNE from both algorithm design and system design perspectives. We have three design goals. First, scalable. We want to embed graphs with 1 billion edges within 1.5 hours. Second, lightweight. We want to occupy hardware costs below $100 measured by cloud rent to press 1 billion to 100 billion edges. 3. Accurate. We want to achieve the highest accuracy in downstream tasks under the same time budget and similar resources. From an algorithm perspective, LightNE consists of two steps, LightNE and spectral propagation. From a system perspective, the LightNE step can be further decomposed into two substeps, that is, parallel specifier construction and parallel randomized SVD. Now we introduce them one by one. The input graph is maintained by a highly optimized graph processing system, GVDS, which provide high-performance graph operations such as performing random walks, querying vertex degrees, random accessing a neighbor of a vertex, etc. In the parallel specifier construction step, we run parallel path sampling with edge downsample. For example, we first sample a uniform random edge UV here. Then, with probability P equals to 1 over the degree of U plus 1 over degree of V, we conduct path sampling algorithm and add the sampled edge U prime V prime to the specifier with adjusted weight 1 over P. Also, with probability 1 minus P, we discard this sample. One can show that the downsampling, which is in essence an application of importance sampling, reduces number of samples required from O(m) log n to O(n) log n, but still preserving the theoretical advantages of specification. Next, we turn to how the specifier is constructed and represented in memory. The path sampling algorithm generates many weighted edges. We need to count them and aggregate them. We found that the fastest and most memory efficient method across all choices was to use sparse parallel hash. The construction used in this paper is folklore algorithm in the parallel algorithm literature. After the construction of the specifier, we conduct parallel randomized SVD on the specifier, implemented by highly optimized Intel MKL library, including efficient sparse dense matrix multiplication, dense matrix multiplication, QR decomposition, and singular value decomposition, etc. The top singular vectors form the initial network embedding matrix. Combining the above steps together, we get the accelerated NetMF. The final step is to perform spectral propagation on the NetMF embedding. This technique was proposed in the ProNE paper and is able to enhance the quality of existing network embedding. The method applies a filter to each column of the embedding matrix using a low-degree polynomial in the normalized graph Laplacian matrix. And the coefficients of the polynomial were chosen to be the coefficients of the Chebyshev polynomials. We now conduct extensive experiments to compare LightNE with other methods, such as graphite, PyTorch graph, NetMF, and ProNE. Limited by space, in this talk, we mainly report the comparison to NetMF and ProNE. We conduct experiments on the open academic graph, consists of 67 million nodes and around 1 billion edges. For LightNE, all experiments are conducted on a server with 88 cores and 1.5 terabytes memory. A similar server, if run in Azure, costs $13 per hour. Vary the number of samples drawn by LightNE, denotes the one with fewer samples as LightNE is small, and the one with more samples as LightNE large. We have 3 observations. First, LightNE large achieves 15 times speed up and a significant performance gain comparing to NetMF. Second, not only does LightNE small run faster than ProNE, but also outperforms ProNE significantly. Moreover, it takes LightNE large around $20 to process open academic graph, meets our design goal to occupy hardware costs below $100 measured by cloud rent to process 1 billion to 100 billion edges. We use another figure to illustrate the comparison to NetMF and ProNE, as well as the efficiency effectiveness trade-off curve of LightNE. Overall, LightNE is a Pareto optimal solution that strictly dominates ProNE or NetMF. For either ProNE or NetMF, one can find a configuration of LightNE in Figure 2 that is both faster and more accurate. Moreover, there is a clear trade-off between efficiency and effectiveness in LightNE. The more samples LightNE draws, the longer time it takes, but higher F1 score that it achieves. That means a user can configure and adjust LightNE flexibly according to his or her time and cost budgets and performance requirements. Comparing LightNE to NetMF and ProNE also suggests that spectral propagation plays the role of standing on the shoulder of giants. The quality of the enhanced embedding heavily relies on that of the initial one. We also conduct experiments on 2 very large graphs with billions of edges. Hyperlink 2014 graph is one of the largest public available graphs today, and very few graph processing systems or graph algorithms have been applied to a graph of this magnitude. We want to emphasize that none of the existing network embedding systems can handle such large graphs in a single machine. We gradually increase the number of edge samples until it reaches the memory bottleneck, that is 1.5 terabyte memory of the single machine. As we can see, the more samples we draw by edge sampling, the higher accuracy LightNE can achieve in the link prediction task. For each experiment, LightNE needs fewer than 2 hours for training, again showing the scalability and the lightweightness of LightNE. Moreover, the trend of growth shown in Figure 3 suggests that the performance in these datasets can be further improved if we can overcome the memory bottleneck by, for example, using a machine with larger memory or designing compressed hash table and linear algebra tools. Now, let me conclude this work. We propose LightNE, a cost-effective, scalable, and high-quality network embedding system that scales to graphs with hundreds of billions of edges on a single machine. We introduce 4 techniques to network embedding for the first time. 1. A new downsampling method to reduce the sample complexity of NetMS. 2. A parallel graph processing stack GBBS for memory efficiency and scalability. 3. Sparse parallel hash table to maintain the matrix specifier in memory. 4. Intel MKL for efficient randomized SVD and spectral propagation. Thanks for your listening. If you are interested in LightNE, please visit our GitHub repo.